Okay, so do you remember when we had that conversation and I said entropy could be defined in multiple ways and in multiple scenarios? So I do not like to call it disorder, like you might have heard in many ways, like entropy is just a disorder. This is the reason why I do not like to call it disorder. So can we please read the story? It is a very easy read. It's going to be fun, but it's essential that we do read it. And I will stay quiet now, or at least try.
11.5 Statistical entropy. It is thought, somewhat incorrectly, that thermodynamics developed before the development of atomic theory. In reality, both theories developed simultaneously. The first book on applied thermodynamics was published in 1859 CE by Rankine. The same year, Maxwell published his first paper on the dynamical theory of gases. So we can say that thermodynamics, statistical mechanics, and kinetic theory of molecules developed together. However, the similarities and interdependencies between thermodynamics and atomic theory were not clearly understood until much later. This led to Maxwell's famous problem called limitations of the second law, posed in his book titled Theory of Heat that was printed in 1872 CE. Maxwell introduced a thought experiment to illustrate the difficulties that arise when trying to apply the second law of thermodynamics to molecules.
Remember, molecules were newly invented things? Keep that in mind, right? People were not aware that these solid things that we see that are very continuous are actually made up of tiny particles that are individual. Right now, we're so used to this concept of molecules and atoms that it's like, oh yeah, so what's the big deal? Go back and think about how weird that was for the people of the time. Make sense? And then also on top of it, these laws that they've come up with don't necessarily apply to these things that they've just come up with. Okay, next.
Maxwell and his thought experiment. In his thought experiment, Maxwell made up a fictional character, which was later called Maxwell's demon, by Lord Kelvin in 1874 CE. Maxwell assumed that this demon was capable of sorting molecules based on the temperature difference of the molecules themselves into hot and cold molecules. The second law of thermodynamics says that in an isolated system, the entropy of a system either remains the same or increases, but never decreases. In creating a difference in temperature, the demon apparently violates the second law of thermodynamics by decreasing the entropy of the system. According to the 0th law of thermodynamics in chapter 1, we know that when two objects of different temperatures are brought into thermal contact with each other, after a certain relaxation time, they both attain the same temperature and are said to be in thermal equilibrium with each other. Maxwell assumed in his thought experiment that one container is divided into two sides and called the right side, side A, and the left side, side B. There's a trapdoor between the two containers, which is guarded by our demon, as seen in figure 11.5a.
Okay, hold on. Let me show you figure this. And there's a tiny demon who's guarding the trapdoor. It took me a while to make that demon, okay?
That's very demonic.
And it was so cute, right, at the end, when I finally figured it out. Do you guys realize that I'm using the same, the ears are the same molecules and the face is the red molecule and the body is black? It's literally those molecules combined together to make the demon.
What's behind it?
What's behind what?
What is this?
It's a tail.
Or
Or a trapdoor.
Yes.
Or that.
No, I'm sure that is the trapdoor, but
Yeah.
behind it, yes.
Oh, this thing? It's just a wand that he's using,
Oh, it's a
Oh, that's
wand.
great.
holding.
It's the sorting wand.
Yeah, the sorting
The
wand.
demon sorting wand.
Yeah, but it can't be like a fairies have that thingy with the star at the end, right? He has to have something, so can't be nice because he's a demon.
Right.
But anyway,
He said that the container is initially filled with a gas temperature T, The demon has the authority to open or close the trapdoor at will, but is bound to follow the following rules. 1. When a faster than average molecule from side A hits the trapdoor, the demon opens it and allows it to go to side B. 2. When a slower than average molecule from side B knocks at the trapdoor, the demon lets it pass from side B to side A.
Okay, next.
The demon follows these rules precisely, and after a little while, we observe that the average speed of the molecule from side B increases, while the average speed of the molecule from side A decreases.
So pause for a second. Do you understand what's going on? Good. Moving on.
We know that the average molecular speed corresponds directly to the temperature. This means the temperature on side A decreases while the temperature on side B decreases, as in the figure 11.5b.
Right here. Right? So this side got hotter and this side got colder.
This implies that our demon is actually a molecular disorder. It allows molecules to pass through the trapdoor such that it produces a temperature difference. The gas on side A becomes colder while the gas on side B becomes hotter as time goes by. This is contrary to the zeroth law of thermodynamics, which states that two objects with different temperatures will reach thermal equilibrium when they are brought into contact with each other. It is worth noting that at this point, we could start a heat engine that operates between two temperatures, which could, in principle, deliver work continuously as long as the demon continues to work as shown in figure 11.6.
So pausing, going to 11.6. So that's the engine that we're putting in. Okay.
In this system, we will get a heat engine that operates in a cycle and converts all of the input heat into useful work. Maxwell imagined that his demon itself did no work. He imagined it as a reversible agent that releases energy when the frictionless trapdoor opens and recovers expended energy when the door closes. Please note that in this case, the second law of thermodynamics is still violated. There are many suggestions on how to build a device that violates the second law. However, no one has ever been able to build one successfully. The question to think about is, how should we deal with the molecular disorder called the Maxwell demon? The easiest way would be to say that there is no such thing as the Maxwell demon, but it's easier said than done after all. The microscopic world is more mysterious than we know.
Next.
Maxwell postulates that his demon was
Intelligent
and could do with the individual molecules. This might be the key to success. To do this, let's start by consider another
scenario.
Let's start with our original component, still divided into two parts, side A and side B, and trapdoor in the middle. However, this time we one side with gas, and the other side be completely working.
Mm-hmm.
This time, suppose the door is created by
a ninja,
whose job is to keep eyes on the door and the gas molecule as seen in the figure 11.7.
Okay, let's go to 11.7. Well, where did it go? There you go. This little ninja is guarding this trapdoor this time. Side A and side B.
Experience tell us that if we open the door, the gas expand and fill the total volume of the container. The question is, how long does the ninja have to wait until the gas is on and to its initial location, which had all particles inside A and complete volume inside B. Since the gas molecules are in continuous motion, you can conclude that there is a limit.
Albeit
a very, very tiny, but no zero possibility that at some time the origin configuration is reproduced. Now, if that happens in a major closed circuit door immediately, and we get a state of lower entropy than the system and originally. However, you believe this will actually happen or not? Represent a process
seemingly at odds.
And the second law of the thermodynamics. It is also important to note that in this case, the ninja has to continuously monitor the system and close the trapdoor at just the right moment for this work.
Do you understand the difference between the two scenarios? In the first case, Maxwell demons continuously open and close the door, right? So as soon as a molecule will come that was faster than average, he opens the door, lets it through. If it's lower temperature comes in, it opens the door and it lets it through. What's the job of the ninja? He just has to wait. And as soon as the initial scenario with all the molecules being on one side and all the non-molecules being on, like a vacuum on one side is achieved, his job is to close immediately. Now, again, recognize that this will not be something that we will experience in real life, right? But there is a possibility that this could happen. A tiny one, but a non-zero one.
It's like the possibility of it being.
But it's not zero. Right? But it's not zero. So same thing here. What is the likelihood that all of the molecules will choose to go to side A? Small, but not zero. That's what we're talking about. Keep that in mind. Okay? Got it? Okay, next one. Sorry. Yeah.
Where are we?
Right here.
For both hypothetical processes presented above with the demon or the ninja, there are some common characteristics. Both processes use the idea of molecular ordering and an agent to monitor the process. In the case of Maxwell's demon, the ordering was done on the basis of the speed of the molecules, and in the case of the ninja, ordering was done in the sense that molecules were collected from a larger region in a more restricted region of space.
So 2 words to note. What are the 2 words that we have used? Probability and ordering, sorting. So keep those words in mind. They're going to be very important. Sorry.
These are only 2 ways out of many ways that ordering could be achieved. Ordering could be done on the basis of the size of molecules or mass of molecules when the system is made of a mixture of gases. In this case, the demon or ninja could open or close the trapdoor in such a way as to separate the molecules on the basis of a particular type of molecules. In short, ordering is very important in statistical thermodynamics. Molecules left to their own devices will not become ordered, and we need an external agent, demon or a ninja, to do the ordering for us, which increases order in the system and reduces the entropy of the system. This leads us to the obvious conclusion. Increasing order corresponds to decreasing entropy.
Oh, appreciate these words. Can we say those again?
Increasing order corresponds to decreasing entropy. All we need is a method of expressing order or disorder in a quantitative way. Maxwell demons sort molecules on the basis of some particular information. That is, the demon will not act until he knows some particular property of the molecules, for example, the speed or the size of the molecules. Even a ninja, as in the second case, just sits around and waits, and while waiting must always be informed continuously about the locations of molecules. Otherwise, he would miss the opportunity to close the trapdoor at the correct time. There are 2 ideas that come out of these observations. 1, there has to be some connection between entropy and information. 2, the information gathering activities of the demon and the ninja may be the key to whether or not the demon and the ninja can do their work.
Excellent.
This link between information and entropy has been exploited and developed as it falls under the heading of information theory, which is very important in the design and application of communication systems. The fundamental equation of information theory is identical to the equation of entropy in statistical mechanics. This might lead to confusion of the quantity we calculate that tells us the information content of messages is also called entropy. In statistical mechanics, we calculate the properties of matter by applying statistics to a large number of molecules. In information theory, we find the information carrying capacity of communication systems by applying statistics to a large number of messages.
Can we read these lines again? There is a whole field that developed that's called information technology. There are textbooks written on information technology. And the fun part is that they all base on just these two fundamental concepts, ordering and probability. Can we read this last all together, these last four lines? In statistical mechanics,
we calculate the properties of matter by applying statistics to a large number of molecules. In information theory, we find the information carrying capacity of communication systems by applying statistics to a large number of messages.
Get it? And in both cases, it's called entropy. And the difference is that what you are using it on changes. When you're using entropy to calculate information about molecules, you call it statistics, statistical thermodynamics. When you're using the same to do it for messages, you call it information theory. The first time I realized that, I was like, whoa, I know a thing.